Kristen Atchison here, and we're talking about Chapter 13, the chemical senses, perceiving odors and tastes. And this is our first lecture talking about odors and adaptations. So odor is a chemical sense. Odor and taste both are. Odors is the sense of olfaction. And it tends to be really kind of underappreciated in people. We don't seem to talk about it as much as an important sense as compared to sight or hearing. We kind of underreport how important it is. Just like other senses, it's sensitive to adaptation, and we'll talk about that in this lecture. And like other senses, there's many, unlike other senses actually, there's many more kinds of receptors. So in vision we had rods and cones. Here we're going to have tons of different kinds of receptors, and we'll talk about that in lecture 2. And in lecture 3, we'll talk about gustation, which is perceiving taste. And we'll also talk about the role that smell and olfaction play in that relationship with taste. So what is an odor? Odor is really the olfactory system detecting molecules. So basically you can kind of think of it, and we'll show you this in the next lecture, and it's in the crash course video as well. It's kind of like a key and lock system, similar to the neurotransmitter system. We have different kinds of receptors, and they're sensitive to different kinds of odors. And certain molecules will fit that key, and certain molecules won't. And so if they're sufficiently concentrated, we're going to detect that it's there. An odorant is, again, molecules that the olfactory system recognizes, and they're going to respond to them differently. So again, there will be different kinds of receptors, and they're going to be sensitive to different kinds of molecules. And this will allow us to perceive different kinds of odors. And again, a molecule, just back to our earlier science knowledge, is just 2 or more atoms that are bonded together by electromagnetic forces. And so again, it's just a combination of the different elements that are making up these different molecules that we as humans are sensitive to. So we talked about thresholds kind of throughout the class. The detection threshold for odor is when we're just able to notice that something's there. So this is the minimum concentration at which you notice that smell is there or that odor is there. This is not being able to recognize what that smell is. This is not necessarily being able to identify what it is, but you're noticing a smell. There's all of a sudden you're detecting something. The absolute detection threshold is when you're able to recognize what it is. You're able to say, oh, well, that's this or that's this. It's going to be a little bit higher concentration, still the minimum concentration, and this is, again, where we can recognize it. So we're going to have a detection threshold for just being able to say, hey, there's a smell. And then we're going to have an absolute detection threshold where we're able to identify what that smell is. And our different threshold is just like it's been all along, the kind of proportion that we have to notice a change in that odorant. How we measure this is through an olfactometer. It looks like a fancy tube system. And basically what they do is they can calibrate the number of molecules in this humidified air, and the participant can able to say they smell something, they don't smell something, they can recognize, they don't, they can tell a difference in it. And we see that we have some information on the differences on how sensitive we are to different things. So for vanilla, which is the first one, we're very, very sensitive to that. We only need, a very, very small percentage, and that's ppm, parts per million, in the air to be able to detect it. Whereas something like chlorine, it's going to need to be a lot more to be able to detect that. So again, we'll see differences. And then we have methanol, which we have, it needs 141 parts. So we see a very big difference in the different kinds of smells and how sensitive we are to them. For this is that absolute detection threshold, the minimum concentration at which we can recognize something. And this will be different depending on the different kinds of molecules, depending on the different kinds of odorants that we're dealing with. And some of this has to do with the olfactory system itself and the different kinds of receptors it has. So when we're identifying and discriminating odors, the source, the distance, and the area all affect that concentration. Because we're talking about parts per million in the air, if you're in a smaller space and you spray that perfume, it's going to be a lot more impactful than if you're in a really large room that has a lot of air and you're across the room and that perfume's sprayed. So the distance from that odor is going to play a role. Again, the concentration of it is going to play a role. The source of it, the area that you're in, all of these things are going to affect the concentration. The more concentrated it is, the easier it's going to be able to detect it. Because, again, we'll get higher parts per million. Where the less concentrated it is, the less likely we are to detect it. Again, as we saw on that previous slide, which was table 13.1 in your textbook, that there really is a difference between the different kinds of odorants, and that's on page 431. That again, so for some things like vanilla, we're going to be a lot more sensitive to that than we are going to be for other things like acetone. So again, there's going to be this kind of difference within the olfactory system that also affects this. When we smell something without context, that identification's a lot more difficult. So if we're given a smell without the context of it, so like vanilla is easy if you're baking cookies, right? You're like, oh, well, that's vanilla that I'm smelling because you have the context around it. But if you're just getting, vanilla when you're out in the woods, without that context, it would be harder to discriminate and be able to identify that that is vanilla. Our experience plays a big role in this. So this is going to have definitely some top-down ability here, where our training and our experience, our previous relationships with these things, or previous experience with these, will affect how good we are at identifying these smells, how good we are at discriminating these smells. So if it's a smell that you're very used to, you grew up smelling a lot of, it's going to be a lot easier to detect that. Whereas if it's a smell and an odor that you're not familiar with, it's going to be a lot harder for you to be able to identify that because you don't have that same level of experience. Now, our olfactory system is really impacted by a lot of different things. Our olfactory system is actually one of the older senses, and we see that different things can affect it. So age, this first graph here, image A, shows the decline in olfaction. So this is being able to identify odors. And we see that we see a decline for both males and females according to age, okay? So those receptors are going to be less sensitive and we're going to be less able to make those detections the older we get. Diseases can really affect this as well. So allergies can play a role. Different medical conditions can play a role in this as well. Things that we have control over, like smoking, can also play a really big role. That's image B. We see this kind of relationship between A, how long someone smoked, and B, how long since they stopped smoking. And so we can see that we lose a lot of that olfaction through smoking, but it can be gained back through quitting. So again, the smell system is going to have a lot of different factors that can really affect how effective that system is. Smell is really an early warning system. So when you first smell something, you are going to be able to detect it better, you're going to be able to identify it better. But as we talked about, we can adapt to odors. Just like we adapted to light, just like we adapted to sound, we're going to adapt to odors as well. So when you first smell something, you're going to notice it very, very much. If you walk into a house and somebody's baking cookies, again, you're going to be able to detect that very, very quickly. Now, the longer you're in that space, the less you're going to be able to you're paying attention to that because you've adapted to this. So we have this responsiveness to change. So what we have here in this graph is we have an odor that we're adapting, in this case, a rat to. So they give this rat this smell, and the rat checks it out the first time, and this is how long the rat spends looking at it or smelling it. So the first time, the rat smells it for about 11 seconds, 10 to 11 seconds. Really, really interested in this smelly thing in the cage. They take it away, they reintroduce it, Second trial, we are down to, about between 8 and 9 seconds. And this goes on and on and on. To the fifth trial, we're down below half of that original investigation. Okay, so the rat is less and less interested in this, has adapted to this smell. This is going to be similar to kind of habituation, this adaptation. They give a new smell. This is the red bar, this test odorant, and the rat's interested again. So again, the rat lost interest in that smell that he was becoming used to, but is again noticing this change to something new. So again, we adapt to this constant stimulation. We're going to, again, if you have a smell in something, different buildings have different smells, and the longer you're in them, the less you smell them. I know in my own particular house, I can be out of town for a long time and I'll come back, and my house smells different to me when I come back than it does when I've been there for a long time. And that's that adaptation. I become adapted to the way the house smells versus when I've been gone for a while. So again, we'll notice these things differently depending on how long we've been have this stimulation. The other thing that the smell system does, the olfactory system does, is what's called cross-adaptation. And this is the idea that we have reduced sensitivity to similar odors. And this occurs in, again, our olfaction system. So this graph here, what they did is they adapted, again, a rat to, in this case, acetic acid. And they got the rat adapted to it. They got the rat down to, about 5 seconds interested into this. Then what they did is they presented the rat with similar odors. And in this case, these are similar in terms of their molecular structure. And the more similar they were in terms of molecular structure, the more similar the rat was in terms of his adaptation. Wasn't as interested, a little bit more interested, but not as much. And then they gave the rat a very different smell, which is this yellow line here, this acetate. And that rat noticed that that was very different. That was a very different molecule. It was very, very different. Now, however, this doesn't work that easily in humans. It's not always based on strictly molecular structure. We can have some things that have similar molecules, but have different perceptions of smell. So for us, it's going to be more what we perceive as smelling alike, that we can have this cross-adaptation. So this is the idea that adaptation to one smell will cross over into another smell based on its similarity. For rats, it really has a lot to do with molecular structure. For us, it can have both molecular structure and just our perceived similarities as well. So this ends our lecture on odors and adaptations. Thanks.